Okay, our next presentation is from Paul Ziemkiewicz. Paul received his PhD from the University of British Columbia and an MS and a BS from Utah State University in the biological sciences. After graduation, he worked with the Alberta Department of Energy, leading its mine reclamation program before coming to West Virginia University to serve as director of its Water Research Institute. The institute develops and carries out environmental research projects in the region and nationally. Research focus areas include management and treatment of waste streams from mining and oil and gas development. Major programs include acid mine drainage, coal ash, water use in power generation, rare earth recovery, coal mine reclamation, industrial wastewater treatment, and watershed restoration. Please welcome Paul.
Well, thanks for inviting me up to the conference. It's been a while, but I think my first trip to Butte was probably in the late 1980s, and I've been bopping in and out of Butte. Know a lot of friends here. I think I heard Ted Duane ask a question a second ago. Anyways, is Ted here? Anyways, someone sounds a lot like Ted, by the way, so take that to the bank. That's right. Anyways, so one of the things we've been doing in our program started about 6 years ago when the Department of Energy sent out a request for proposals for any ideas to recover rare earth or critical minerals. In fact, they only started out on rare earths from mine waste. And specifically what they had in mind was fly ash and coal refuse. In the East, refuse is tailings everywhere else in the world, but I'll say refuse. But think of rejects from the coal cleaning process. And as a result, and I've worked a lot with both, and they're pretty recalcitrant materials, particularly fly ash, which is a aluminum silicate glass. Okay, so no. So I asked DOE if we could look at something interesting like acid mine drainage, which we do a lot of work on and have been working on for a lot of years. And I had previously gotten some samples from some friends of mine in the industry. And sure enough, the stuff is loaded with rare earth elements. And I'll get into the rationale behind all that in a few minutes here. So, but one of the things that's really exciting is that we've done a lot of work since if there's acid mine drainage anywhere in the world, I've probably been there, so hellholes are my specialty. And that includes hard rock as well as coal. Now, the Department of Energy, since that money happened to be from the fossil energy program, wanted coal, right? So we've been looking for a way to get a demonstration project in the hard rock arena, and we recently got that opportunity from the Department of Defense, the IBAS program. So we got an announcement of an award recently. Whether we can successfully negotiate a contract with DOD remains to be seen, but we remain optimistic. That would be a good-sized project to install a rare earth recovery unit at the Horseshoe Bend AMD treatment plant at Montana Resources in cooperation with Mark Thompson, who I'll be going out to see later today. So that's the Berkeley pit there. The Horseshoe Bend plant is up in the corner here, right around here, and collects water from the Yankee Doodle tailings and the Horseshoe Bend Creek, treats it here. Rejects go into the Berkeley pit. Otherwise, water goes into the processing facility over here. And we all know this graph, and this is what occasions all the interest from the federal government. We used to have a dominant position in rare earths, namely Mountain Pass in its early configurations. And that's been taken over by People's Republic of China in recent years, and we need to get our supply chain act together again, and that's why the federal government is so interested in this. So starting out a long time ago, we put together a team. You may have noticed that my degree is in the biological sciences, by the way. I am not a mineral processing engineer by any means, so I know when I'm beat. So we got some really good mineral processing engineers and economists on the job, Aaron Noble from Virginia Tech, and also Tom LaRochelle, who recently got a PhD from Aaron, but has his own company now. So Tom is one of our partners as well. And he's worked in the private sector for most of his career, plus a number of other partners. Montana Resources, Ted Dwayne, Rockwell, who provides us with a lot of our process control automation system. So one of the things we made a point of not doing was simply doing a lot of lab bench type of research without thinking about how to scale this up to commercial operations. So that's why we work with SNF Chemicals, Solmax, Rockwell, and people like that who could listen to us talk about a problem and say, of course, being professors, we think we can figure out everything from scratch, which takes 15 years. And they say, we have one of those off the shelf, and it's better than what you're thinking of, by the way. So we were able to go from bright idea to this facility here. That's our, what we call the A34 plant. And that's actually not just a proof of concept, but it's an operating facility now. We've been in operation and production since last September. And it's a acid mine drainage treatment facility built by our state government at this bond forfeiture site, which is an old coal mine. The company went bankrupt. They forfeited their bond to the state. The state is responsible for picking up their NPDES permits, the only state in the country that somehow or another got themselves that imposed on themselves. But at any rate, so they're in the business of building a lot of high-grade AMD treatment plants. And so we partner with them. And we work very closely with the state, and we said, listen, if you guys are going to build one, what's the next one in queue? Because we want to scale this up with this DOE funding. And so we did, and we built this together, this 500 GPM AMD treatment plant with rare earth recovery on the back end of it. And you'll notice it's all under cover, so people can't fly balloons over it, for instance. Oh, yeah, I forgot to mention, yeah, we have a lime silo. Anyways, you all know about acid mine drainage, comes from pyrite. In coal, coal-related pyrites are the most reactive pyrites in the world. They're kind of like pyritites. They're not hydrothermal crystalline pyrites that take a while to get moving. These are thin sheets or pollen grain size bits of pure pyrite. And as soon as you expose them, they go bananas. They oxidize almost immediately. And as a consequence, we have all kinds of problems with acid mine drainage. It's our biggest pollution problem in the Appalachian coal basin. The typical approach to treating acid mine drainage in the past is to put in what were called passive treatment systems, using a lot of getting limestone in the way of these acid mine drainage discharges coming out of a big, this could be a 600-acre complex, underground mining complex that dips in this direction. So get it in touch with a lot of limestone and maybe knock off half the acid load before it gets into a creek. So that's kind of doing the Lord's work, but not exactly making any money doing it, and kind of treating the creek and making something better way downstream. Here's another example over here of a company project. It's a company that we work with near Morgantown, where we're located. AMD comes down here off their property. There's a doser down here, in this case a caustic doser. And the sludge goes out into this pond, and every once in a while you can see this dredge goes back and forth and scoops out all this sludge. Well, and the sludge goes up into these geotubes here. Those are Solmax geotubes, again, one of our project partners. And that passively dewaters all this sludge, and this is really important because the chemistry of knocking rare earths out of solution is about as difficult as taking aluminum out of solution. They all act like transition metals, and they have about the same pH tolerance range. Dewatering is the trick. So passive dewatering is really important for us. Now, when we started out this whole idea way back, before we knew Solmax, we ordered actually a plate and frame press. Crazy idea. You drive yourself nuts running plate and frame presses. So we got up to this point. Now we can dewater to the extent that we need and just pump this stuff up into the bags, and periodically they dry out to the point where they meet spec, and we would haul them away. But first of all, we need to separate the rare earths from all the junk. And the junk mainly consists of aluminum, silicon, and silicon is not a regulated metal. So people who work in acid mine drainage don't pay a whole lot of attention to silicon, but half of that junk out there is silicon. And then this one doesn't particularly have a lot of iron in it, that's why it's white. But we get a lot of iron and other junk. We do not want to have to process that in the plant. When we started out the whole idea, DOE wanted a minimum feedstock grade of 300 milligrams per kilogram, parts per million. So we had to go with this stuff, which was fairly concentrated, and we were able to get our hands on it right away. But there's a lot of unreacted lime, unreacted base, whatever you're treating it with, plus you have to dissolve all that aluminum and all that iron in order to get the rare earths into solution. Then you have to separate them. Really big nuisance. So what we decided to do is alter the process to eliminate a lot of the junk. So this is our history so far, proof of concept back in 2016. And you can see we're unidirectionally moving towards commercial operations. And so we just got 2 awards recently. The demo hit HSB, Horseshoe Bend, and we also got another phase 1. This will be a class 3 feed study that'll be funded by the Department of Energy. And 2 awards were given out by the Department of Energy. We got one, and University of North Dakota got the other one. And so we will be competing with each other to see who comes up with the best class 3 feed study and the best economics. We've already done a class 4 feed over in here. And we've already built a full-scale demo at 500 GPM. So we think we've got a pretty good chance. The feed study, the class 4 feed study, had very favorable economics, and I'll get into those in a minute too. So this is the basic idea. AMD comes in, remember the lime silo? But you have to have a liquid lime feed in order to be able, unless you want to put in 2 lime silos, which cost $750,000 each, so you generally want 1. But you have 2 feeds, and again, you bring in pneumatically hauled and distributed lime into the top of the bin, use makeup water to make up a slurry. That goes to mixer A. Mixer A brings the pH up to about 4.5, and then everything that we don't want drops out, or most of what we don't want drops out as reject and goes to in-mine disposal, which is really important because this stuff, in coal at least, is RCRA subtitle D. All these treatment sites, and there's hundreds of them all over the Appalachians, are already permitted to dispose this stuff on site, and you can basically just use it as soil amendment if you want to. But that gets rid of most of the iron, aluminum, and silicate. And then we also have, so the decant from that clarifier goes into mixer B. That brings it up above 8. And at that point, the rare earths and cobalt precipitate out. We dewater that in our geotubes. We get something called PC, or preconcentrate. That goes to acid leaching solvent extraction, and we get our concentrates. So that's the basis of our technology. One of the neat things about acid mine drainage, by the way, this is a really neat thing, because you just heard that previous presentation, which was fascinating, but you notice how much of the low value rare earths, the light ends, cerium, lanthanum. So here's cerium, lanthanum. So all the gray are the light rare earths, and all the red, and then the colorful bits are the ones that we like, the heavies. In particular, we also like neodymium. We always get about the same proportions of everything in acid mine drainage. And I'll show you how preposterous that gets after a while. But you can actually see the Otto-Harkins effect here too. Odd, even, atomic numbers. So neat little trend there. I love geochemistry. But anyways, so that we almost always get this 45-55% split with the heavies to lights, which has a lot to do with the value of our process. So again, old-time acid mine drainage treatment. You got an old UST full of caustic, doses a pond. Pond kind of produces decent water. And this is our process. I'm showing this because you can scale this down to something that's remote, unpowered, out in the middle of nowhere somewhere, like a lot of our AMD treatment plants. And it's using geotubes, and you collect them now. And again, and here's your MPDS discharge point. Now, all of this that I've been talking about so far is under US patent. So we have a utility patent in place for this process. We want people to use this technology, but we want to make sure that the concentrates made in this process wind up going to a central facility in the United States that will be paid for by the taxpayer's dollar and hopefully supported by its revenue and taken over by the private sector. But we do want that feedstock to stay inside the country, and that probably will be the basis of the licensing business, and that's mainly why we protected that technology. And here's a geotube in action. You pump in slurry and you get cake out of it. So we can get these filter cakes if we really want to up into the 85% solids range. We kind of like something a lot lower than that just because the economics really don't favor that much. Here's our plant that's under construction. You can see the 3 clarifiers in the mystery lime doser over here. So again, when we treat this stuff, our initial pre-concentrate is something you could swim through. 0.5% solids, good luck hauling that anywhere. It's not going to pay for itself. So a lot of our technology is the passive dewatering. Again, we can bring it up to brick, we call them bricks, 85% solids. And then we take this pre-concentrate after it's been dried, because you don't want to acid treat all this water, because you just consume a lot of acid, which is your biggest M&O cost, of course. And then you take your concentrate, acid leach it, and you get really weirdo versions of manganese species. We think this is manganese 6. You never see manganese 6 in real life, but so that's why we get these goofy colors like this. And we can get the concentrations up pretty high, and then we go into MREO manufacturing through another, we have a couple of provisional patents governing this process, and then we've been able to get up to 95% mixed MREO. The processes that we're starting up now will then do the elemental separations on the MREOs and then reduction to metal as needed. And a lot of that is conventional technology, which is why we worked up at the head end of the whole process all along without getting into the downstream processing. Again, a lot of that's off the shelf. So, something got squashed here. Anyways, this is our typical PLS here. This is our PLS. This is the elemental composition. But this is the other stuff that we're generating. So we get a lot of, we've identified a list of critical minerals for DOE's purposes that we'll also be separating and that we include in our value proposition. So that's lithium, cobalt, nickel, zinc, and manganese, mainly focusing on, as you noticed, battery metals, which are in high demand. So back to Horseshoe Bend. This is what we'll be doing. These are our tasks. Very conventional stuff. Here's the Horseshoe Bend treatment plant, which is perfect for our point of view because it has 2 clarifiers, really big clarifiers, a lot of flow, and a really high-grade AMD. So the concentrations of rare earth at Horseshoe Bend are roughly 10 times what we normally see in coal. So just for comparison purposes, and about 10 times the flow. So it doesn't take many of these to add up to a good size number. There's a close-up of the clarifiers. There's one, this one's down for refurbing. And you see the independent pH controls on them. Anyways, all of this goes toward a supply chain for a central refinery. And the central refinery would then take in concentrates that meet our specs. So it's just like a sawmill. I used to work in a sawmill. Sawmill sets out specs. We want lodgepole pine. We want DBH of this. We don't want too many knots or splits in this stuff. And if you show up at my operation at my mill meeting these specs and our graders are happy with what you've got, you'll get a check in this amount. Bye. Okay. That's basically our supply chain concept. Dairy farms, soybean processing, a lot of the agri world operates under this kind of supply chain. So, but it's not like mining, where you have a permit, a lease, a mine on site. And we've looked at a lot of these. We've also talked with the EPA Superfund, and they've sent us samples from a lot of places around the country, like Iron Mountain, California. Of course, we've got our own inside operation going at Butte. Four Corners, this is the, they've got 3 different names for it. One that blew out into the San Juan River a couple years ago. And we've looked at a lot of coal sites. The idea is to get a transportable concentrate that can haul into a central refinery. Naturally, my favorite senator would like that to be in West Virginia. just guess. But here's what the amounts look like. If you're used to dealing with coal or bulk commodities, limestone, these will look like trivial numbers. But just based on what we know so far, and operating under the restriction that DOE gave us that when we put together the supply chain estimate, only 50% of the total amount could come from non-coal sources. So you see 323 coal gives you about this. Different concentrations of stuff. We got plus cobalt and manganese in this particular analysis. 6 hard rock mines give you the same amount. So I'm sure people have already figured out what this all amounts to. Anyway, so we got a pretty robust supply chain. What we don't have, though, is a domestic refining capability. So you got this concentrate. We do not want to do what Mountain Pass is doing, which is send the goodies off to a foreign country for processing. We want that value added to happen here. So this is basically where we are right now. Defense needs about 1,200 tons per year of total goodies. We can supply, I think, most of that. The other important thing about rare earths is that they're not all created equal. Some of them, like the light rare earths, even at really high grades, don't really fetch a real high price. So cerium, lanthanum, we wouldn't even recover these. That would go into the reject pile or stored for future use or something. What we're really excited about are some of these bad boys over here in the heavy category. And you're looking at particularly terbium and dysprosium. We can generate a lot of that. And those, to a large extent, contribute to our overall supply value. Anyways, this is the thing that really knocked me silly when I saw this the first time. And it happens over and over again. So this is not just a one-off, but this is a very consistent pattern. If you can tell the difference between coal AMD and its rare earth distribution, and this is actually the Berkeley pit, this one, and all the other hard rock mines we looked at look pretty much the same, let me know, because it's the same stuff. Now, what does vary, sometimes something will have more yttrium than the others, but it's just more yttrium. But anyways, this is very encouraging to our economists because they say, now we have a consistent feedstock. We don't have to throw a switch on the plant every time a new truck comes in and change the process around. Basically, we got milk, raw milk coming in that meets our specs. So here's our plant up at Mount Storm that I showed you from the outside before. And I'm not giving away any IP here because basically this is your conventional lime silo, 2 feeds on it, 3 of our rectangular clarifiers under cover. And this was our first production back in September. And the concentrates go out to the geotubes. This is the inside of the plant. And this is what comes out of the geotubes. That stuff is it's just been sitting out there maybe 25% solids. Just a little more drying, and that'll be ready to put in a truck and haul somewhere. Our process starts with acid mine drainage, which doesn't even show up here in terms of concentrations of various goodies like, or the rare earths and then 3 of our criticals. The total reject metals are the blue. And so our process, if you just take AMD sludge, this is what you're dealing with. Something that's mainly junk and a lot of manganese, but almost very low concentrations of rare earths, for example. So we go through sludge A, which knocks out the bulk of our gang metals, and then sludge B, where we start getting enrichment, and then we go to our leach residuals and mixed rare earth oxides, and now we're up in the high clover, so to speak. So this is another thing, and this is getting into a sort of watershed restoration kind of practice here. Maybe 6 years ago, we put together a plan for our DEP because they had to build a whole bunch of individual treatment systems for a lot of bond forfeited sites up in this one big watershed that's, by the way, not very far from Morgantown. And this watershed was polluting the daylights out of the Cheat River, Cheat Lake, big recreational, obvious stuff. Yet DEP was spending something like $2 million a year maintaining and operating these worthless little plants to get into NPDES compliance at each one, putting really good water into a stream that had a pH of 2.5 and having 0 effect on the watershed. So we said, that's stupid. why don't we just get a pipeline company, which we brought in as a partner, Southwestern Energy, to build some pipelines from these big underground complexes that were feeding these. And by the way, they were all pre-law, abandoned mine lands by definition. And that was where all of the pollutant was coming from, and feed them into a central plant and abandon these guys with the at least temporary compliance of EPA. And that has recovered 19 and a half stream miles. This is now a fishery. Muddy Creek is a fishery. The Cheat River, 7 or 8 miles of Cheat River, and all of Cheat Lake, which is another 8 miles, is a fishery now. It was completely dead before. Anyway, so the DEP likes this idea so much that they want us to convert this existing plant, which was not made for rare earth conversion, into a rare earth unit. And it's indicated we already have the right kind of lime silo, just 2 pH controls, and we've got goodies coming out in our geotubes. So we'll be working on that also in the upcoming years. And these are some of the results from our pilot plant. And these are the rare earth oxides that we're producing. So very high purities. We were able to separate lights and heavies at the plant itself without doing anything more. We developed a new kind of high throughput solvent extraction facility. And this is what we're getting on our light circuit. And that's, this is 94% all rare earths, light rare earths. And then our, which one do we have here? So this is its distribution relative to everything else, 94%. And then the heavy rare earths look more like this. And so we had a lot of reject metals, and we were working on ways to get rid of those. But we're getting up to a couple weeks ago, we were up to 65% rare earths without a whole lot of difficulty. So really nice high grades. And when we recover, when we reject the useless metals, we're not losing a lot of the rare earths themselves. In fact, a lot of markup on these. And this is the light circuit, heavy circuit. So this is how this is Tom Rochelle's design. This is how our central refinery would look. Circuits for things that are useful. And this is the value proposition from different circuit options. We kind of like this one over here. And our net present value. My economist friends tell me these are very nice numbers. And again, this is the one we like the best over here. MM means mish metal, which is lanthanum and cerium, which we would reject. And this is looking at, because the other thing about rare earths is that the prices fluctuate like crazy because the volumes on the market are so small at any one time. So we looked at a distribution over time over the last 15 years. This was these gray are the minimum values we saw over that whole period. These are more typical values, and they've been going up in recent years. And at that point, your net present values are up in this range. And this is a waterfall plot showing the relative contribution of each one of our products. We just don't make every rare earth in the world and dump it on the market. You'll never make money doing that. But these are different items. In some markets want the oxide, some want the metal, different grades and so forth. So the contained value is up in the almost $2,000 per ton range. That does not account for transportation, processing, and refining. But nevertheless, I'm told those are pretty good numbers. More economic stuff. So the disadvantages are that it requires a lot of sites, need to manage the supply chain, quality control, moisture grade, low concentrations. One of the nice things is, these are all nice things, we don't have any RADs. If you'll recall from your geochemistry, uranium and thorium don't go into solution until the pH gets down below 1, which is why if you have a bastnäsite or a monazite deposit, you have to drive the pH down below 1 to get that matrix to come apart. We don't need to do that. Nature does all the acid leaching for us, and I've never seen acid mine drainage anywhere that is below 2. So they just don't go into solution. They're not there. We don't have to worry about them. Okay, so I think I'll stop there before I get yelled at.
Oh, you're doing great.
Okay. Yeah.
All right, questions from the group?
I was just curious on your, I think it was your Muddy Creek project. That's the Cheat River tributary.
Yes, yes, indeed.
What was the time frame from, basically a watershed that had no fishery to a fishery?
Oh, like 3 or 4 years. And most of that was construction of the the clarifiers. But once the clarifiers turned on, it was almost immediate.
Any other questions?
Thank you for the presentation. Just a question about the refining. Is there plans to build a plant
Oh, yeah.
in the U.S.?
Yeah, so the recent award announcement from DOE, again, there were 2 awards given in the United States, one to us, the other to North Dakota, would be for a national refinery, a centralized refinery. Cool. So the first step is that phase 1, and that'll be the class 3 feed study. If that's successful and accepted by DOE, then we move to actual construction of the plant. And there's money in the budget to actually build the plant.
Cool.
It'll require a 50% cost share, so if anyone's interested in $100 million to spend.
Thank you.
Sure.
What was the cost on your pilot plant, or the 500 gallon per minute plant you were talking about?
Oh, above and beyond what DEP would have spent anyways on building the plant. It was basically 1 extra clarifier, which was about $250,000, and miscellaneous equipment, so yeah, maybe $1 million. And the revenue on that, I'm not sure if I included that slide here. I did not. Yeah. The revenue for that particular plant, just on that 500 GPM flow, would be something in the range of about $140,000 a year in revenue, assuming we had the market and the refinery and everything else was in place. Their lime cost, which is their biggest O&M cost, is something in the range of $50,000 a year.
Earlier, you said that you guys sampled some of the Gold King acid mine drainage. Did you guys find any rare earths in that?
Yes.
You did?
Yeah.
Oh.
Yeah, if you want a rule of thumb, if the pH is below 3.5, it's probably pretty decent.
Recoverable, you think, amounts? Or?
Oh, yeah.
Oh, great.
Now, it depends on how they configure their final treatment system. So they were still in the process of thinking it through and designing it when I was talking with the EPA.
Any other questions?
And the other thing is, if you want a quick assay, if you take the concentration of total rare earths in milligrams per liter, and multiply that by flow in gallons per minute, and multiply that by the Ziemkiewicz constant, which is 0.002, that will give you tons per year of rare earths, or anything for that matter.
So one question on the potential refinery, would that be available to take? Because I know there are commercial enterprises out that are, moving towards process for oxide production. So would that be able to take commercially produced oxides from other to further refine?
Yes, sir. That'd be one of the ideas behind it.
Wondering what, if any, radioactivity or radioactive minerals might be associated with the concentration of the rare earth elements?
Oh, the pre-concentrates, DOE requires us to do a uranium and thorium assay on every sample we do. And it's usually in the low tenths of a %, which is not far from background.
Any other questions?
You had mentioned a remote option for these facilities. How big are we talking for those centers? These look like pretty large scale facilities, but I thought you mentioned there was a remote or a smaller option for.
Yeah, and when I say remote, I mean just basically almost like something that you come by once every couple of weeks and look at, right? And top up the caustic tank. But yeah, if you got a caustic feed drip, and so we're actually putting in a demo of that exact idea right now. We'll turn it on in the spring, but we've got most of the background work already done. So what kind of quality control we can promise, I don't know yet until we actually run it theoretically it should be great, but real life is always different.
Question, what kind of contribution do you think this will make toward meeting the U.S.'s need for rare earth elements? What kind of scaling up would you have to do? And if it would meet that, how soon in the future do you predict?
The Department of Energy's goal is to have this program be able to provide the wherewithal to make 10% of the national requirement within the next 6 years, maybe. And it would take that long to actually build the central refinery and get all the upstream pieces in place. So yeah, but the 10% of the national requirement. And you saw from that one graph I showed, that's the total requirement is something like 26,000 tons per year. A lot of that, though, comes into the United States as manufactured products. So it would be a matter of reshoring a lot of that. And that would also handle most of the Defense Department's requirements. One of our project partners is Northrop Grumman. And this is an interesting story. So they just called me up out of the blue, say, well, yeah, we're interested in working with you guys. And it turns out that they make lasers, among other things. But the laser industry, they just require oxides. Not that that's a trivial matter, but they don't want refined into metal. So there are certain suites within this that I didn't get into detail here, where we would have a circuit specifically for making oxides for the laser industry. And of course, that's all defense too.
All right. Thank you.